Here is an example. We have RLC series circuit. The question he's asking about: find the total current and voltage drop across each element and also draw the vector diagram. That's the given question. So in any AC circuit, the first thing we need to do is we need to convert the given circuit into the given time domain circuit into frequency domain. How do I know this is time domain circuit? In time domain circuit, you have a sinusoidal wave. L is going to be in Henry, C is going to be in Farad. So we need to convert them into ohms and the maximum value into RMS value. So I'm going to draw another circuit. This R equal to 500 ohm. We call this as JXL, which is J omega L. I know omega value. Minus JXC equal to 1 over J omega C. And here always convert this into RMS value, because in our regular life we always use the RMS value, not the maximum value. Okay, at an angle of 0. 0 came from there. Okay, so XL equal to omega L. We know omega is 377 times L is 2 Henry. We'll end up with the 754 ohm. Okay, so remember, this is called inductive reactance. This inductive reactance is always a plus J, 754 ohm. Okay. And capacitive reactance is always XC minus, it's always negative number, minus JX equal to 1 over J. 2 times 377 micro is 10 to the power of positive 6 in the numerator. You will end up with 1326.27 minus J. Okay, so this is minus J 1326.2 ohm. Okay, now this circuit is called a frequency domain circuit. Okay, now you have the frequency domain circuit. Okay, now we need to convert this frequency. Now we're going to find the total impedance. So impedance is nothing but it's a complex number. It opposes flow of current in AC circuit. It opposes flow of current in AC circuit. Okay, it opposes the flow of current in AC circuit. So Z value is 500 plus J. Everything is in ohms, so we're going to add them directly. 754 minus J 1326.2. So at the end we'll end up with 500 minus J 572.25. Oh, that's the impedance. Remember, this is in rectangular format. We need to convert that into polar format. So when I convert this into polar format, that value is 759.91 at an angle of minus 48.85. I mean, most of your calculator should be able to do it. I'm going to do it one more time. To get the magnitude, just 500 square plus 572.25 whole square. That's the magnitude. And theta is tan inverse of imaginary number over real number. Okay, that's theta. And one more thing you need to remember, once I moved it into frequency domain, I always use the capital letters. Okay, so now I equal to V over Z. V, this 169.7 over square root 2 must be 120 volts. 120 divided by, or 120 at an angle of 0 divided by 759.91 at an angle of minus 48.85. Okay, here I found I equal to V over Z, which is 0.1579 at an angle of 48.85, and voltage drop across resistor is 78.95 at an angle of 48.85. This is in polar format, I'm converting that into rectangular format. When I convert this rectangular format, this is the voltage. Now voltage drop across inductor I times JXL. Okay, so 0.1579 at an angle of 48.85. JXL is 754 at an angle of 90. That is 119.05. So VL is minus 89.64 plus J is 78.34 volt. And VC, that's voltage drop across capacitor, which is I times minus JXC. Okay, I is 0.1579 at an angle of 48.85. XC is 1326.25 at an angle of minus 90. Okay, 209.41 at an angle of minus 41. So when I convert this into rectangular format, 157.68 minus J, 137.8 volt. Now when we represent them in the circuit diagram, or if you connect a voltmeter here and measure the voltage, for sure you will see the magnitudes. The first one I have 78. This is the magnitude. We will see 78 volt, and here we'll see 119 volt. Here we'll see 209 volts. Those are all RMS values, not instantaneous values. Okay, remember that. Now how come our supply voltage is only 120? How come this is showing you 209 volt? That is because the inductor and capacitor, they both store energy. Now, but when inductor is storing energy, this is dispersing energy. When capacitor is storing energy, inductor is dispersing energy. So when capacitor is charging, it's not only getting energy from the source, it also gets some energy from the inductor. So that's the reason the voltage is going to boost up to 209 volts, even though our supply voltage is 120 volts. Okay. But when we add them, we need to add vector sum, not arithmetic sum. Okay, because the KVL must valid in AC also. So when you are doing KVL equation, we have to do the vector sum. So V total equal to VR plus VL plus VC. VR we have 51.95 plus J 59.45, and VL minus 89.64 plus J 78.34 plus J 78.34 and plus 157.68 minus J 137.8. So 59 plus 78, these two must be cancelled out with this. 51 minus 89 plus 157, we will end up with 120 at an angle of 0. That's the voltage total. Now I'm going to draw the vector diagram. Vector diagram, we always take the V reference, voltage as a reference. So here is the coordinate system, x-axis, y-axis. We also call that as imaginary axis. Okay, the given voltage V is 120 volts is right there. That's the given voltage V. Okay, now we are I equal to 0.1579 at an angle of 48.85. So plus 48, I is going to be somewhere here. Okay, that value is, the angle here is 48.85. Now VL 119.05 at an angle of 138 plus 138. So it's going to be somewhere here. That's VL. For sure, the angle between these two must be 90 degrees. And VC is going to be exactly opposite. Okay, I'm not drawing according to the values, because VC I have 209, VL we have 119, and this angle here is minus 41.15 degrees. Basically, the angle between I and VC must be same 90 degrees. Okay, this is the vector diagram for RLC series circuit. Okay, thank you.